We will start with the radar principle, then we will see how an FMC waveform looks like. After that, we will explore how to estimate the range of a single target. We will extend the same idea to estimating the range of multiple targets, and we will do the same for velocity and angle. And finally, the conclusion. When faced with an unsolvable problem, change it into one you can solve and solve that one instead. These are the excellent lines Fred Harris wrote in his book Multirate Signal Processing for Communication Systems. And we will see how FMCW radar is a really beautiful example of this principle. From intuition, we should estimate the range of a target through the time delay. We emit a waveform and we record the time of arrival of the signal back to the receiver. And from there, we can estimate the range. But we will see that this method is less accurate and more expensive. And instead, we can change this problem into estimating the frequency of a sinusoid, which is much simpler and more accurate to do. There is another application of this principle that we will see within the presentation itself. So radar stands for radio detection and ranging. It is an extension of human sensory perception. For example, we have eyes and ears, which are continuously processing the signals already present in the environment. A radar changes this in two respects. One, it actively transmits a signal into the environment and hears for the echoes. And second, it does not really have to use the same frequency range. It is not using only the visible light range like our eyes. It can use the RF range, and for sound we can go beyond the audible range as well. The presentation today is on a particular kind of radar, which is frequency modulated continuous wave. It is very useful in short range applications such as self-driving cars, intrusion detection, heartbeat monitoring, and vibration measurement in industrial and residential products. So how does a radar work? It emits electromagnetic energy into the environment and looks for the echoes or reflections. For example, in the case of self-driving cars, we have these emissions, and on the return of this signal, the car radar can process all the signals and see where the targets are. For a continuous wave, the transmit signal is given by xt equals a cos 2 pi ft. We are just considering the simplest type of radar, which is a CW radar. The delayed signal is given by a cos 2 pi f t minus t naught. So there are two things to consider here. What? The frequency does not change, but the amplitude has become very weak. That's why we have different A and AR. And secondly, the phase has changed by a parameter phi. This phi is given by minus 2 pi f naught. So we can see that this delay contains the information about the range from the target. How? Because from the laws of physics, this tau naught is given by 2d naught, which is the double the distance, one for going to the target, the other for the coming back. So 2d naught over c, where c is the speed of electromagnetic wave. And from lambda is equal to fc, we can write it as minus 4 pi d naught over lambda, from where the radar computes the distance as lambda over 4 pi phi. So this is very good, but CW is not useful for ranging. Why? The reason is that the phase of the signal is periodic with 2 pi. So the radar on the return echo cannot really differentiate between the 90th period or the 97th or the 110th. They all look the same. Its acquisition range, its estimation range is only between 0 to 2 pi. That is why CW is not useful for ranging. But it can be used to determine the velocity. If we do the same derivation with a moving signal, then we get the expression as v is equal to ft over 2 lambda, where ft is a Doppler frequency. There are many other drawbacks in CW as well, not only the limited range within 2 pi, but also there are many other drawbacks of the CW radar as well, which we will not discuss, but we'll move on towards an FMCW radar, which is a CW but modulated with linearly changing frequency. An FMCW block diagram starts with an FMCW waveform generator. The signal goes through the transmit chain and the power amplifier and then into the air. On the return path, we have a low noise amplifier, which is the signal, the output of which is down converted with the local oscillator, and then we have a filter, analog to digital converter, and then DSP processing. The focus of today's talk is on this DSP part. So for that, we need to know IQ processing. IQ is not a complicated concept. Just like a complex number has two parts, real and imaginary, and a sequence of numbers is basically a signal. Similarly, an IQ signal is a sequence of complex numbers. We have a real part and imaginary part. In this case, we are showing it's a complex sinusoid, which is CW in complex domain. Its instantaneous phase is given by phi equals 2 pi ft, and the waveform has an expression e raised power j 2 pi ft equals cos 2 pi ft plus j sine 2 pi ft. This is known as Euler's identity. So it is that cos 2 pi ft is the projection of the waveform on real plane. Imaginary waveform is the projection of this wave on the Q plane with time. So we modulate a CW, and we need to see what is the effect of modulation. Modulated signal bandwidth is no longer a single impulse in frequency domain. Instead, we have a large bandwidth signal. But remember that for ranging perspective, a narrow signal in time domain is more desirable. Why? Because when multiple echoes are arriving from a target, then we need to have them separately arriving at the receiver. Otherwise, they will all jumble up and we will lose the actual range of the target. So when a narrow signal in time domain is desired, but from an RF circuit design perspective, generation and processing of a high power short duration signal is very difficult. Now, the question is how to have a short time duration signal with minimal complexity. The answer is very interesting. The idea is that all the signals arriving at the receiver are processed by a filter. So the output of the filter needs to be narrow in time domain, not necessarily the signal itself. To illustrate on this idea, let us look at this animation. Here we can see the transmitted signal, received signal, the output of the match filtering process, and the match filter output. You can see that the transmit signal is not a single impulse, it's not something very narrow in time domain, but the match filter output is showing us a peak. With some more processing, this peak can be refined and made more accurate. This peak brings us to the processing gain. If you are familiar with the direct sequence spread spectrum systems, and even if you are not, I will invite you to have a look at this figure and see in the top case, the aligned case, we have a sequence of plus ones and minus ones, which is a signal. And the top diagram is echo and the bottom one is match filter output. If you see in the figure, they are perfectly aligned with each other, which means that plus one is being multiplied with plus one and minus one is being multiplied with minus one. So minus one times minus one is also plus one. Once we integrate the whole signal, the whole waveform, the answer will be a long summation of plus ones. So it will give us a high peak. On the other hand, for an unaligned case, this minus one is multiplied with a plus one with a minus one, and so on. So essentially, we have a random stream of ones and minus ones. And when we add them all up during the integration process, we will have a low number. This is the idea behind processing gain. So how is this done in an FMCW radar? The FMCW waveform is not a stream of plus ones and minus one, but instead a linearly changing frequency, which is why it is called frequency modulated continuous wave, linear uh, FMCW. So here you can see that in the top case and bottom case, again, we have an aligned case and an unaligned case. In the aligned case, the waveform exactly matches the match filter. The returning waveform, the echo, exactly matches the match filter, and the frequency is being multiplied with a similar frequency. We will have a high peak. I will just tell you how. In the unaligned case, the frequencies are not matching with each other and we will have a low case. The reason is that assume the frequency is not changing. So we have a one frequency wave cos 2 pi f1t, another frequency cos 2 pi f2t. When you multiply with them from trigonometric identity, we can have cos 2 pi f1 minus f2t plus cos 2 pi f1 plus f2t. Now you can see that when the frequencies are not similar to each other, then over a summation, over an integration of a long sequence, this they will be just an area under the curve of a cosine, which will essentially go towards zero. But if the frequencies are exactly aligned, so f1 minus f2 will be 0, we'll have a constant number, cos 0 is 1. Over a long integration of ones, we will have a very high peak as shown in the top figure. Let us see now how an FMC waveform looks like. The mathematical expression is given by e raised power j pi mu t square. This is how the diagram is in IQ plane. And look at the projections on the real and imaginary planes. The imaginary projection is sine pi mu t square and the real projection is cos pi mu t square, much like the complex sinusoid we saw before. But instead of changing linearly over time, the phase is changing quadratically over time, which means that it is getting faster and faster, and the signal seems to be compressed more and more to the right side. It is similar to how we define speed as the rate of change of distance and acceleration as the rate of change of speed. Let us see the two-dimensional view now. The chirp is nothing but a linearly changing continuous wave. This spread the spectrum. Why? Because now if you look at the figure, it has both low frequencies and high frequencies. Although they are existing at different times, but still the signal contains both low and high frequency, and this is known as chirp spread spectrum. This is an example of an upchirp, which means that the frequency is increasing with time. Where does this bottom graph come from? To see this is the conventional FMCW curve, and this expression is given by xt equals e raised power j pi mu t square plus 2 pi ft plus theta. Previously, we only focused on the mu part, the acceleration part. Now we are including the complete expression e raised power j pi mu t square plus 2 pi ft plus theta, which includes frequency and phase as well. So if we see the rate of change of instantaneous phase and divided by 2 pi, we get mu t plus f. And this is what we can say here. With time, this slope is given by mu, the acceleration of the phase. Now the waveform does not have to be an up chirp always. It can be a down chirp, which means that it starts with a higher frequency and then the frequency is linearly decreasing. This is more visible in this bottom graph where we can see that the signal is going from a higher frequency with time towards a lower frequency. Another option is a triangular chirp where we have both an up chirp and a down chirp. At the start, the signal is increasing in frequency. After a certain time, it comes downwards, which means the frequency starts decreasing. This duration during which the chirp is produced is called a sweep time. And on the frequency axis, we can see that the signal bandwidth is represented by B here. So from here, we can find the chirp rate, which is obviously, as we said before, is the slope related to the bandwidth and sweep time, which 0 to B means B over TC. That is the definition. And that is how we decide what kind of chirp rate we need to incorporate into the signal. The units of the chirp are hertz per second, which can be seen from the above expression, but mostly in practical applications, because the frequencies are high and the sweep times are low, so it is megahertz per microseconds that is used. Now we are ready to jump into how to find the range of a single target using an FMCW radar, which is a very interesting topic. So the radar transmit a frequency modulated continuous wave, which we saw is given by e raised power j pi mu t square plus 2 pi ft plus theta. The return echo is obviously shifted in time if we plot this on the same graph. Now there are many ways to find the delay, but I will choose, because the purpose of this presentation is to make things as simple as possible, I will choose the simplest possible geometrical route. But there are other ways like the DSP approach or other. We will see them either here, or you can see that in the FMCW article on my website. So for similar triangles, we have this small triangle which is similar to the bigger triangle angle. From here we can see that tau naught over TC, the delay divided by the sweep time, equals to FB over B, the beat frequency over bandwidth. And what is beat frequency? If we draw a signal, we could obviously see it more clearly, but here when the signal is shifted, the frequency that changes, because it is mixed with the same signal at the transmitter side, The shift determines how much the beat frequency will be. And we can find it as tau naught equals TCFB over B. With the delay known, all we have to do is plug in 2 d naught over C again here, and we find d naught equals C TCFB over 2B, where we use, instead of tau naught, we use 2 d naught over C, 1 d naught for the signal going to the target, the other d naught for the signal returning from the target. And from here we can see that this beat frequency exists after the delay towards the sweep time. Now in this expression for the distance, the range estimation is that simple. C is known, it's the speed of the electromagnetic wave. TC is the sweep time known. B is the bandwidth known. But how do we know the beat frequency? FB is not known. How to do that is we have to write it in the DSP form. A delayed waveform is given by, remember, the transmit waveform was given by xt equals e raised power j pi mu t square plus 2 pi ft plus theta. The delayed waveform can be found by just replacing t with t minus tau naught. That's what we will do here. Replace t with t minus tau naught. And when we simplify the expression, we see that after the complex mixing process, because mixing happens with the same phase and frequency, e raised power minus j pi mu t square plus 2 pi ft plus theta at the transmit side, and we find the expression e raised power j minus 2 pi mu tau naught plus pi mu tau naught square minus 2 pi f tau naught. Now this does not depend, the right expression does not depend on time. The second expression also does not depend on time. Only the first expression depends on time. So we say this as 2 pi f b t plus phi. We conclude that the mixing process gives us an output which is a simple complex sinusoid. Remember, e raised power j 2 pi f b t plus phi is nothing but a simple complex sinusoid. I have a simple typo here where after j we should have a bracket, and this is the signal part. You can see that e raised power j pi f b t plus phi is given by a waveform, and the spectrum of the mixer output is a sinusoid, a sinc function at the frequency fb. Now the question is how to find the frequency FB. Now sinusoid in noise, it's a classical estimation problem that has, if you explore, you'll find research papers from 1970s, 1980s, 1990s, 2000. Basically, it's a problem that we can assume is thoroughly researched, and we have very accurate solutions. Once FP is known, it can be put into this expression and we can find the range of a single target. So how to find the range of multiple targets? Because in the environment it's not necessary that there will only be one target be present. There can be many different targets. So for example, if there are multiple targets, the cumulative signal, remember, the in the case of a single target, the waveform was given by e raised power j 2 pi fpt plus phi. So for multiple targets, it will be fb naught, fb1, and fb2. We have three different targets in this case, and the cumulative signal is given by this expression. Here, pause for a moment and think, how can we find three different frequencies? We just had a complex sinusoid in noise problem solved, and now we have three sinusoids in noise. How can this be solved? And it turns out that the echoes, they are given by three different time delays, each of which corresponds to a certain frequency, three different beat frequencies. The cumulative signal is now can be seen through this waveform, where it is not a complex sinusoid, it is not a simple chirp, but it is a combination of three sinusoids. If you look at the horizontal and vertical projections, you can see these on the complex real and imaginary planes. So we have multiple beat frequencies, and the best known process we know is the discrete Fourier transform. We yk equals summation n equals 0 to n minus 1 yn e raised power minus j 2 pi k over n, and where k over n is the normalized frequency, and we can see the real part of the mixer output. When we take the spectrum of this signal, which consists of three different frequencies, we can see The first frequency on FP0, second on FP1, and third on FP2, where the magnitude of the frequency here depends on the return signal strength. So here is a summary of the TSP processing. We have a transmit chirp and multiple receive echoes are arriving. The cumulative signal is a sum of sinusoids, as you can see in this second figure. After taking the FFT, we will have peaks according to each beat frequency corresponding to each target. Once the beat frequency is known, then using the knowledge from sweep time and bandwidth, we can find the range of each target from this FFT output. Recall that in the start of the presentation, we said when faced with an unsolvable problem, change it into one you can solve and solve that one instead. That was a quote by Fred Harris. So now here we can see its easy application. The target ranges are not being found through time delay estimations, but through beat frequency estimation, which is much more accurate and easier to do. We have changed the problem of time delay estimation to frequency estimation. Both of them give the same desired result, which is actually the distance estimation or the range. The second thing is that remember that a CW can measure the velocity of a signal, but not the range. By velocity means a target is moving. Only when the target is moving, then a CW, simple CW radar can measure the velocity. Now, if the target is not moving and we have to estimate the range, what we can do is we move the signal because the target is not moving. We move the signal how? By using a chirp. It's a linearly changing frequency. So we move the signal, and by using this principle, we can find the range of a stationary target through an FMCW radar. After looking at a case where the range of a stationary target is measured from an FMCW radar, the question is what happens when the target starts moving? So our beat frequency shifts by Doppler frequency. These are the two cases I'm showing in the figure. On the left side is a positive Doppler frequency. On the right side is a negative Doppler frequency. So on the left side, for a positive Doppler frequency, the actual frequency difference comes out to be FP minus FD. Obviously, on the right side, for a negative Doppler, this would be FP plus FT. The problem here is now that there are two unknowns in one equation, both FP and FT. So we cannot separate the Doppler frequency from the beat frequency. The question is what to do in this situation. One solution is to have another equation where we have two equations in two unknowns which can be easily solved by linear algebra. So we introduce a triangular chirp. As we saw earlier, the triangular chirp is for half the sweep time, the frequency is rising. For half the sweep time, the frequency is falling. This means that the first half of the sweep time, we get FB up, and for the second half of the sweep time, we get FB down. Now we have two equations with two unknowns within each sweep time. The first equation during the rise period is FP up equals FP minus FT. The second equation during the fall period is FP plus FT. These can be easily solved, and now the problem is apparently solved. The problem here is that what happens if there are several multiple different targets? Do we devise a chirp which goes up and down several times during a sweep time? This is not an efficient solution. So we do something else. Let us see what. For this purpose, we refer to another quote from another great communication scientist, and that is never discard information prematurely that may be useful in making a decision until after all decisions related to that information have been completed. Let's see how we can apply this to this problem. So the problem is we know how to find the range of a target from an FMCW waveform. But what happens when two objects are in the same range? Their return signals will overlap, and we will not be able to know that these are actually two targets or multiple targets, not one. And we want to do this through the simple FMCW waveform we saw before. So the solution lies in remembering the phase, which we totally ignored in our previous discussion. Phi is given by pi mu tau naught square minus 2 pi f tau naught. Now, if you write tau naught square as pi mu tau naught times tau naught, we can see that the first expression is the evolution of phase through the chirp rate, and the second one is the evolution of phase due to the frequency. Okay, so at time t is equal to 0, the FMCW radar transmits a chirp, and assume that the car is stationary. The return signals will come back with a certain phase which is given by this expression. At time t equals to tc, that is at the next sweep time, the FMCW radar emits another chirp. Since the car is stationary, the phase is the same. No phase difference between these two different chirps. But if the target moves by delta d, a very slight movement, which is given by VTC, where TC is the sweep time and V is the velocity of the car. Why sweep time? Because the second chirp is going after sweep time. So the difference in distance, the movement of the car will be given by delta D equals VTC. We can write the delay of the signal, returning of the signal, as 2 delta D over C. Note that this is not the delay of the signal, is the delay in the second echo. So we can say that this is the delay difference. So delta tau, not tau naught. This is a very important point to remember. This is not tau naught, this is delta tau, which is given by 2 delta t over C and hence 2 VTC over C. To see the effect on phase, we first draw the waveform. So the first chirp at the receiver and the second chirp at the receiver have a very small phase difference that is governed by change in delay delta tau. And when we put this tau naught plus delta tau expression in the original expression for phase after some derivation, the result is given by the phase at second instant is given by the phase at the first instant plus negative 2 pi mu delta tau t plus pi mu delta tau square plus 2 pi mu tau naught delta tau minus 2 pi f delta tau. So 4 extra terms, 1, 2, 3, 4. Let us consider the effect of these 4 terms on the phase. Now, apparently, by looking at this expression, we think it looks like a hopeless case. It's too complicated and it doesn't look like we can extract the velocity from such a complicated expression alone. But this is the difference between a mathematician and an engineer. The mathematician only looks at the expression. The engineer looks at empirical results, like what will actually happen in the real world. And then we try to exploit what happens in the real world to gain what we want from minimum resources. Let us consider the following parameters as an example. Speed of EMA, we already know approximately the speed of light, 3 into 10 raised power 8 meters per second. Suppose this is a 77 gigahertz radar, sweep time is 40 microseconds, chirp rate is 40 megahertz per microsecond. The range is 20 meter, FMCW short range, and velocity V is given by 36 kilometers per hour, which turns out to be 10 meters per second. Let's put these expressions back into the phase and then find out the result. The term, we'll do this term by term. Term 1, which is minus 2 pi mu delta tau t. I'm calling it a beat frequency in the sense that mu delta tau is a change in frequency times time. So it is sort of a beat frequency. That comes out to be 107 hertz. But the phase from one chirp to the next only changes by 2 pi mu delta tau tc, because of the effect of tc is nearly equal to 0.02 radians, a really small value, 0.02 radians. Term 2 contribution is given by pi mu delta tau square, which is 9 into 10 raised power minus 10. Certainly we can ignore this term. Term 3 can also be ignored because 2 pi mu tau naught delta tau turns out to be 4.5 into 10 raised to power minus 5. Finally, the fourth term, I will just show you again. First, second, third, and fourth. The fourth term is minus 2 pi f delta tau. That turns out to be 1.29 radians. So that is the significant contributor. 10 raised power minus 5 ignored, 10 raised power minus 10 can be ignored, 0.02 radians as compared to 1.29 radians can also be ignored. So we can write the change in phase from one chirp to the next. Important point, one chirp to the next is given by minus 2 pi f delta tau. From here we can find the change in, we just basically need to replace delta tau by 2 delta d over c, where delta t is the small difference the target moved from one chirp to the next, and hence we can write 4 pi delta d over lambda, and from here we can write the expression for v as v equals lambda over 4 pi delta phi over tc. So what we have gained here is that we know the range of the target and we also know the velocity of the target, and in the case that two targets are in the same range, then we can differentiate between them based on their velocities using the same waveform. No modification in the waveform has been done. Now, what does this signal look like after a period of n chirps? This we saw for the first chirp, but what happens after a period of n chirps? What does the signal look like? So from the expression phi 1 minus phi naught equals minus 2 pi f delta tau, we can write phi 1 equals phi naught minus 2 pi f delta tau. And each next chirp keeps adding another 2 pi f delta tau. So this means that after nth chirp, the phase phi n will be given by phi naught minus 2 pi f n delta tau. And what does the signal look like? The signal will be some constant multiplied by e raised to power j and this phase. And what is this phase? Minus 2 pi f n delta tau. And we just saw that this can be written as, and where would we saw this in the previous slide? Here we saw that this can be written as delta phi can be written as 2 pi 2 v tc over lambda. So 2 v tc over lambda, and which is nothing but a complex sinusoid again, but this is not the same complex sinusoid in the range domain. This is a complex sinusoid in the phase, in the we will say when time evolution of phase, will see, we'll call it slow time, but on chirp after chirp the phase is collected and that turns out to be a sinusoid with frequency 2v tc over lambda. Here is a diagram where you can see that after the FFT is taken to seat in the frequency domain, and we can see that we have a phase, a sync signal from that phase, which is changing. So in the first chirp, it is at 0. In the after the second chirp, this is at some value minus 2 pi f delta tau. After the third chirp, it is at minus 2 times 2 pi f delta tau. After the fourth chirp, it is minus 3 times 2 pi f delta tau. So it can be seen as e raised to minus j 2 pi f n delta tau, and the imaginary part is sine, the real part is cos. The interesting thing is that again through the FFT we can solve this problem. So what we have, if there are multiple targets and they are moving at multiple speeds, simple, when we take the phase in the Doppler domain or slow time, chirp after chirp, we will have sinusoids which are adding in that domain, and we have to take now two FFTs. Why? In the first FFT we separate them in the range domain. So if you look at this figure, we have taken the first FFT and now we can separate the targets in the range domain. Although the equation says there are three targets, the diagram shows in the range domain only two targets, which means two out of the three targets are traveling with the same speed, are in the same range. Now, if they are traveling at different speeds, have a close look at the phase evolution. Here you can see that the phase of the first target is evolving at certain pace, but the phase of the second target after the FFT is evolving at two different speeds. So we can see, so this is how we can differentiate between the targets which are in the same range but moving at different velocities. This is a better figure of the same phenomena, where in the range we have two sync signals, one here and one here, and in the velocity, when we take another FFT in the velocity, then that sync signal breaks down into two more sync signals. The question is, what happens when there are multiple targets at the same range and traveling at same velocities? As an example, we can see this where it shows three different targets. Then the direction is the differentiator. If we have multiple antennas, we can use the parallels between velocity and direction. How? Imagine that for a single antenna, for to compute the velocity, we've computed the phase between two consecutive chirps. So that delay turned out to be delta tau equals 2 VTC over C. Now, if we have two adjacent antennas for the same chirp, there will be a difference between the wave reaching to the first antenna and the wave arriving at the second antenna. That difference, delta tau, will be given by delta D over C. And as we will see, this delta D is given by D sine theta over C. We'll see that in the next slide. So here we can that theta is visible. So the it's if it arriving from some distance, the planar wavefront theta is arriving a little with a little delay as compared to the first antenna. So this from simple trigonometry turns out to be d sine theta, and extra distance is traveled and the delay will be given by d sine theta over c. Now, what is the phase shift? Phase shift will be 2 pi f delta tau, which will be 2 pi delta d over lambda, or 2 pi d sine theta over lambda. If we can calculate that, if we can compute that phase shift, we will have a handle on the direction depicted by sine theta. So final expression is given by theta equals sine inverse lambda over 2 pi delta phi over d. So let's see how it is done. The one difference here is sign non-linearity as compared to the previous case, because the waves are arriving at different angles. So due to sine theta, the target, which is within plus minus 25-30 degree range, will have a much better accuracy as compared to the one which is arriving, which is moving at a larger angle from the radar. So for a small angle, for example, close to zero, we can just remove the sine theta is equal to theta, so lambda over 2 pi delta phi over d, lambda over 2 pi delta phi over d. Note that the expression for velocity we found in a few slides earlier was lambda over 4 pi delta phi over tc. How similar are these two? The difference between 2 and 4 is due to the back and forth propagation in the case of the velocity, which is not here for multiple antennas. Otherwise, lambda over 4 pi, lambda over 2 pi, change in phase, d and chirp time. So it's a very interesting parallel, and we can check this non-linearity with our own eyes as well. Right now, you are watching this presentation, and my slide is right in front of your face. If you try to look something which is in the corner of your eyes, it will not be as visible as whatever is in front of your eyes. It's the same. We have our eyes are in a two element optical array. So what will the waveform look like? Again, we will see the phase evolution, and that turns out to be e raised power j 2 pi d sine theta over lambda 1, e raised power j 2 pi d sine theta over lambda 2, e raised power j 2 pi d sine theta over lambda 3, and so on. Eventually, it will be a complex sinusoid with frequency d sine theta over lambda. So we will take an FFT, not a simple FFT in time domain. This will be the FFT in space domain across the samples collected by different antennas. So once we do that, we can have the direction of arrivals from all different targets. When we combine these three FFTs, we have the radar data cube. Range FFT across chirp samples, This is known as fast time, the actual sample rate of the receiver from one sample to the next. Doppler FFT from one chirp to the next. This is known as slow time. This is done after the FFT has been taken across the range samples. And here we can see this in a better figure. Sample by sample signal is arriving at the receiver. We are taking FFT and we are collecting it in a matrix. And when we go across the samples and then take an FFT, then what we get is a range Doppler map. It's where the range is across the fast time, Doppler is across the slow time. This is called slow time because from one chip to the next, and range is fast time because it's exactly the sample rate of the FMCW radar receiver. The third FFT is taken across multiple antennas in spatial domain. This will produce a third 3D result. So we have across each antenna we have a 2D FFT, 2D, and then we take a third FFT across the angle domain, and what we will get is a cube. From this cube we will know the ranges of multiple targets, velocities of multiple targets, directions of multiple targets, and we will not be the targets at the same range or traveling at the same velocity will not be able to confuse the radar into thinking that this is actually one target. In conclusion, a CW radar uses frequency to measure velocity, cannot measure the range. An FMCW radar, what it does is that it measures the range by of a stationary target by changing the signal itself. It from a continuous wave, single frequency, it changes the frequency in a linear fashion. So the frequency is changing. It can measure the range of a stationary target. But the interesting thing is that the same waveform can be used for estimating velocity, but in discrete blocks, that is from one chirp to the next. And if we have multiple antennas, that we can exploit multiple angles of arrival to resolve the directions of the targets as well. This will result in a 3D structure which is known as the radar data cube. As far as the system design guidelines are concerned, you can click on this link and it will take you to an article on my website, which is FMCW radar part 3. And it shows you how to design the system. So we have different parameters: bandwidth, sweep time, chirp rate. There are a lot of things which have to decide. How do we decide? It depends on the real world requirements, and that article explains these things in detail. You can read more articles on wirelesspy.com, which are written for DSP and wireless communication engineers from an intuitive viewpoint. And the good thing is that each article has lots of figures, so it becomes relatively easier to understand. Thank you very much. I'll see you next time.